Chapter 5.6, Differential Equations, Growth and Decay, Day 2. Yesterday we looked at the relationship. The rate of growth of y is proportional to y. This ended up being the exponential growth equation, PE to the RT or CE to the KT or some variation thereof. We're going to look at some other equations that are other ways we work with exponential growth and decay. One of those is Newton's law of cooling. Newton's law of cooling states the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. In a nutshell, dt, the change in temperature with respect to time, equals k times the difference in the temperature, T minus T sub O. We're going to use that equation to solve some differential problems, some growthy problems. So our first problem, y represents the temperature of an object in a room whose temperature is kept constant at 60 degrees. The object cools from 100 to 90 degrees in 10 minutes. How much longer will it take for its temperature to decrease to 80 degrees? We'll start with Newton's law of cooling in differential form. We know the temperature of the room is 6 degrees, so we will plug that into the equation. dt equals k times t minus 60. And now we'll go about solving it. Remember, to solve a differential, you want to get your variables that are the same on the same side. So I'll get my capital T's on the left and my lowercase t's on the right. And now it's a differential, so we'll integrate it. Over here, this is a natural log form, because you got dt over t, ends up being natural log of t minus 60 equals kt plus a constant. We'll work through this. We want to solve for t. We'll undo the log by exponentiating. So t minus 60 equals e to the kt plus c. We'll apply some exponent rules here. Adding exponents, that's the same as multiplying exponents with the same base. So that's e to the kt times e to the c. What we got here, e to a constant we don't know. E is a constant, so a constant to a constant, it's just another constant. So I'm going to simplify that, and we're going to get ce to the kt, which should look familiar to you. Finish solving for t by adding 60. Right? So there is our form, our general solution to that differential. And now we're going to figure out what c and k are. We'll start first knowing that the object starts at 100 degrees. So at time t equals 0, the object is 100. And you can see that c ends up being 40, because this ends up being 1. So c is 40, so t equals 60 plus 40 e to the kt. After 10 minutes, the temperature is 90 degrees. We will plug those values in. 90 equals 60 plus 40 e to the 10k. Subtract 60, divide by 40, we get 3/4 equals e to the 10k. Natural log of 3/4 equals 10k. So k equals 1/10 the natural log of 3/4. So our equation, when all said and done, t equals 60 plus 40 e to the 1/10 natural log of 3/4 times t. And how much longer will it take for temperature to get to 80 degrees? Well, put 80 in for t. 80 equals 60 plus 40 e to the 1/10 natural log of 3/4 t. Subtract 60, you get 20. Divide by 40, you get 1/2 equals e to the 1/10 natural log of 3/4 t. Obviously, you can estimate that to get a value. I don't have my calculator open right now, so I'm just using the whole number value, or the actual value. Log both sides, natural log of 1/2 equals 1/10 natural log of 3/4. Divide. So t equals the natural log of 1/2 divided by 1/10 the natural log of 3/4. We'll calculate that out as soon as we get our calculator open. So the natural log of 1/2 divided by 1/10 the natural log of 3/4. And we'll see it takes 24 minutes total. And so since the question says how many more minutes, the correct answer is 14 more minutes. Let's look at some more differentials. Here's a differential. Y prime equals the square root of x over 7y. Let's find a general solution for y. We can't find a specific because we don't have any other points. So remember, y prime, that's the same as saying dy dx in this case, because the other variable is x, equals x to the 1/2 over 7y. We want to get all the y's on one side, all the x's on the other, so we'll multiply. We get 7y dy equals x to the 1/2 dx. Integrate. On the left side, we got 7/2 y squared. On the right side, we got x to the 3/2 times 2/3 plus a constant. Now, there should be a constant on both sides. What I did is I combined them into one constant, just put it on the right. We'll multiply both sides by 2/7 to get rid of the fraction here. So y squared equals 2/7 times 2/3 x to the 3/2 plus a constant. And I'm not going to multiply a constant by 2/7 because that's going to be a constant as well. So we got y equals plus or minus the square root of 4/10, 4/21, sorry, x to the 3/2 plus a constant. That would be the general solution. More specific solution would have a point to find c. Let's solve this one. This one's in a verbal form. The rate of change of y with respect to x varies jointly as x and L minus y. Well, we all know what rate of change of y with respect to x looks like. When we say varies jointly, it means it's happening at the same time. So we'll say k and then x times L minus y. And you solve this the same way. You separate your variables. Treat L as a constant. So we'll separate our variables. dy over L minus y equals kx dx. And we'll integrate. The left side, you got dy over y, kind of. You got a negative y. It's going to be a log. We're going to have to account for the negative, so it's going to be negative natural log of L minus y equals kx squared over 2 plus a constant. All right, I'm going to get rid of the negative. So natural log of L minus y equals negative kx squared over 2 plus a constant. Don't need to multiply the constant times the negative because it's still going to be a constant. We'll exponentiate to get rid of the log. And we end up getting L minus y equals CE to the negative k x squared over 2. And then finish solving for y. Y equals L minus CE to the negative kx squared over 2. Okay, a couple more examples. All right. Rate of change of p with respect to time is proportional. This one's straight up dp dt equals k times 25 minus t. All right? There's no p variable, so you can just separate, move the dt over, k times 25 minus t dt, and integrate. Integrate p dp, we get p equals k times 25t minus 1/2 t squared plus a constant. There we got it. Distribute k if you want to or not. Does not matter. Okay. Here we have a slope field. We have to find a particular solution to the slope field that goes to the point 0, 1/2. And the equation for the slope field is xy. So we'll start by separating dy dx equals xy. We'll separate, we'll move the y's over and the dx over. All right, you can take a look, you can see that dy when you integrate it will be the natural log of y. Integration of x will be 1/2 x squared plus a constant. We got a log, so we'll exponentiate. Y equals ce to the 1/2 x squared. Remembering that this ends up even e to the 1/2 x squared plus c. You can rewrite it in that form. And then plug in the point to find your c. When y is 1/2, e is 0. And so we see c ends up being 1/2. So our particular solution would be y equals 1/2 e to the 1/2 x squared. All right, so the steps to solving these differentials with exponential growth and decay. Step 1, separate your variables. Step 2, integrate. Step 3, solve for y or p or whatever you're being asked to solve for. Then step 4, if you have it, use your particular solution. To solve for constants and get a specific solution.